In this video we will derive the energy conservation equation in solids in 3-dimensional. For any object we can split it into a number of small objects like this, small cubes like this, and we study each cube as an individual part. Each object will have a q in, an energy in, and an energy rate in and an energy rate out that goes from the object per unit time. So we have q in minus q out equals the difference between the energy that entered and the energy that leaves is the energy stored, but it is energy rate, so it is energy stored rate. If we have energy stored bmcb delta t dt, then we have E dot storage equal mcb d temperature by d time. But we have the temperature of the object depends on x and y and z, which is the position of the object in the 3D space, and also is a function of time. So we can't do total differentiation. We must have a partial differentiation, partial temperature by partial time. So we can replace E dot storage by mcb partial temperature by partial time equals q in minus q out. We need to interpret the q in and the q out. So we will take a look at a 3-dimensional cube. We have here x and y and z. If we take a look at this point is inside the cube. It is at a distance of delta x over 2 and delta x over 2. If we have this as an x, and this point will have an x that is dependent on our origin point of the object that we need. So we have an x. In order to define the function, we have temperature field that depends on x and y and z and time, and we also have a flux field that we introduce in the first part. If we have this plane, this plane that is behind our C, we need to find the energy that goes into it. We define Qx as being the heat that is flowing in the x direction. Qx, what is Qx equals to? We know that Qx at this point, which is at the middle of the cube, equals to negative K A partial T by partial X. We know that Qx is equal to this, but we don't need the Qx at this point. We need it at a point which is delta x over 2 in this direction from it. So we can interpret it as that Qx as a function of x will be Qx as a function of x can be, sorry about that, Qx plus minus delta x over 2 can be interpreted as Qx minus partial Qx by partial x delta x. How we derive it? We will assume that if we take that this is the x and we plot Qx versus x, we will have some function. We don't know about it, but if we zoom in for this closed area, we will see that it is just a line. If we zoom this portion, we will see that it is some kind of line that has a slope that can be determined from partial qx by partial x. So we can interpret it. So we have the slope and the value at this point, qx at x. So if we need qx minus delta x over 2 as delta x approaches 0, we can use the slope formula, the slope approximation from calculus, to say that qx minus delta x over 2 will be equal to qx minus this portion, which is the slope multiplied by the distance we moved, but it is in the negative x direction, so we will have negative. While qx plus delta x over 2 will be qx minus plus partial qx by partial x delta x over 2. The difference between these is that delta x over 2 is here in the negative direction, while there in the positive direction. This is why there is negative here and positive here. We can see that for the back face, we have qx at x minus delta x over 2, while here we have qx at x plus delta x over 2, because we have here moved to delta x over 2, and here we moved delta x over 2, but in the positive and the negative directions. So the signs are determined by this. We can see that qx minus delta x over 2 is inside to the object. It is heat that is added to the object, while q at x plus delta x is q out of the object. We do this because we do that qx, we know that it is in the direction of positive x. It is in the direction of positive x, and we use the law, and what the law gives us will affect which is positive or negative. But we will use the equation that say that qx is negative k partial t by partial x will give us the qx in the positive x direction. If it is negative, it is in the reverse direction, but if it is positive, it will be in the right direction. So we'll assume that it is in the positive direction, and the law will correct it using the gradient of temperature. So we'll have qx at x minus delta x over 2 will be in the object, while that point will be out of the object. So we'll have this as q in, while that is as q out. If we take q in minus q out, we will get what? We will get qx minus partial qx by partial x delta x over 2 minus qx plus partial qx by partial x delta x over 2. Qx will cancel out with qx, and we will left with negative partial qx by partial x delta x, because we have delta x over 2 and delta x over 2. Positive will become negative because of the sign, and here we have negative with negative, negative delta x over 2 minus negative delta x over 2 will give us delta x. So that is the result in the x direction. Similarly, we can do it for the y direction, and we will get negative partial qy by partial y delta y, and we will get negative partial qz by partial z delta z. We don't have to create it 3 times. So we have the 3 energies that we have in the x and y and z direction. Let's interpret it. We will use Fourier's law that we see in the previous video, that say that qx is equal to negative k multiplied by the area multiplied by partial temperature by partial x. This is the law that we will use. Qx is like this, so we have negative partial qx by partial x, delta x will become negative partial by partial x of negative k multiplied by the area multiplied by partial t by partial x. Negative will cancel out with the negative, and we will left with a positive quantity. Let's take a look at the area. What is the area that moves in the x direction? We know that this is the x direction, so the area we looking for is this area. This area is composed of a square that has 2 sides. The first side is moving with the y direction, so this is delta y, while this side moves with the z direction, so it is delta z. So the area that is in the x direction is delta y multiplied by delta z, delta y multiplied by delta z, and we will get rid of the area by replacing it by delta y delta z. Similarly, we can do the same thing for these 3 terms, partial by partial y k. Here the area will be delta x delta z, partial temperature by partial y. Here we will have partial by partial z of k delta x delta y, partial temperature by partial z. These are the 3 new terms. We can put it in the equations. Sorry, we have left, we have lost our delta x, delta y, and delta z. We can arrange the equation we have in the first place that say that qin minus q out equals mcb partial temperature by partial time with this. So we will get partial by partial x k delta y delta z partial temperature by partial x partial by partial y k delta x delta z partial temperature by partial y plus partial by partial z multiplied by delta x delta y partial by partial z k delta x delta y partial temperature by partial z delta z will equal to mcb partial temperature by partial time. We can get delta y delta z out of the equation because they don't depend on delta x and so on. So we will get partial by partial x multiplied by k partial temperature by partial x multiplied by delta x delta y delta z, which we can replace it with delta volume, the differential volume of the object, because we have a cube of delta x delta y delta z. The volume of the cube is the volume of the cube equal to delta x, delta y, delta z. We'll replace it with delta v plus partial by partial y multiplied by k partial temperature by partial y delta v plus partial by partial z multiplied by k del partial temperature by partial z delta v. Delta x, delta y, delta z will be delta v, delta x, delta y, delta z, delta y will be delta v equals to m here can be replaced with rho multiplied by delta v because it is mass equals the density multiplied by the volume. So we'll have rho delta v cb partial temperature by partial time. So we can divide out by delta v, delta v, delta v. We will get partial by partial x of k partial temperature by partial x plus partial by partial y of k partial temperature by partial y plus partial by partial z multiplied by k partial temperature by partial z will be equal to rho cb partial temperature by partial time. If we have a material that doesn't depend that doesn't affected strongly by temperature, by change in position, if we assume that k is constant for those material, we can get it out of the integration like this, and this partial by partial will be a second derivative, partial to temperature by partial x squared, and so on. We can divide by k on both sides, and this term will be called 1 over alpha, which alpha here represents thermal diffusivity, because it is a constant that depends only on the material. K depends on the material, Cb depends on the material, rho depends on the material. So we'll get rid of these three quantities and replace it with one quantity, 1 over alpha, which is the alpha is thermal diffusivity, and we'll get our equation. This equation may be written in more compact form by using the Laplacian operator. We will get 1 over alpha partial temperature by partial time. This is the conservation equation of three-dimensional solids.